Now, in this video, we're going to continue to play with the Keras and the scikit-learn and the TensorFlow frameworks. But now we're going to show an example of how to use a simple feed-forward neural network to predict time series. This is going to be an example of the auto-regressive neural network structure. In order to do this, we're going to first create a function which will generate some data. And this function is going to be basically a low-pass filter, so sort of a first-order dynamic system. The function needs to know how many time steps we wish to produce, for what time we want to run our low-pass filter, and then we can calculate the time steps that step length that we need to generate from those two parameters. A simple low-pass filter in discrete time can be described as follows. So we have a single input low-pass filter, which looks like this. Then the equations in discrete time, we need a coefficient a, which is the time constant divided by the sum of the time constant plus the time step, which is why we need this guy up here. And then we need a coefficient b, which is just 1 minus a. So that's basically the whole low-pass filter. Then we need to make a simulation loop. Of course, this could probably be done quicker and more elegantly utilizing array functions and NumPy and so on, but for the purpose of instruction, this is perhaps more clear. So first thing we need to do is create our arrays, which is going to be of length n rows and 1 column. And then we also have the time, which is useful to keep track of. So like this. And then we simply do a for loop like so, where we say that we have an input u, which is going to be 1 if I is less than n-half, otherwise 0. This is just a Python construct, something called a ternary operator, which takes the value 1 if I is less than n-half, otherwise it's 0. And then we implement our filter by saying that the next, actually we want to loop through n minus 1. So the next value in the time series xi plus 1 is going to be a times the previous value plus b times this u input. For the time, we are just going to do very simply like this, in case we want to use this for plotting or whatever. Probably it's not going to be needed, but we'll just create it all the same. And then we will just return our time vector and our state vector for the low-pass filter. So that's basically the whole thing. That's going to generate a nice low-pass filter time series for us. So to test that, we're going to just do this. And we'll set time constant to 1 second. And then we'll just plot this quickly, like so. So that's now basically our low-pass filter signal, which start out initialized with a state of 0, and then it increases up to some number here. And after 5 seconds, when the filter is in more or less steady state, then we change the input and drive it back to 0 again. So then we get this shape here. And the objective of this experiment is then to try and use machine learning to see if we can learn to represent this kind of time series behavior. And we're going to do this by creating a regression model. To do that, we first need, as we discussed in the video on neural networks, to restructure our data. So we will make a function which does that, takes the input data, and then a number of columns or time shifts. So if you watch the video, you know that one way to do neural networks on time series is to create shifted copies of the data. And I'll show very soon what that means. So the first thing I need is to recover the length of the input data, which I will assume is just one column vector. Then I'm going to create my output matrix, which is just some zeros. And now here comes the trick. So we're going to be shifting the column k times, and each time we're going to lose one data point. So from this video, you remember that when we shift the data, we move the data one step back in time. And in order to do that, it means that we have to discard 10 data points, otherwise we don't have anything to shift. So the shifted data is going to have number of rows equal to n minus k. And to do the actual shifting, we'll just do this in a simple, perhaps not so efficient way, but instructive nonetheless. So we'll just say for k in range k, let my output data, all the rows from column k should then equal to the data. And here comes the actual shift. So we want to take from row k to k plus n minus k. And then we want to do that in row 0. Now the data only has one column, so having the column index 0 here might seem weird, but since this is a two-dimensional array out, we need a two-dimensional array in, otherwise NumPy is going to complain. So that's why we just do this thing here. Then this assignment operation will work. The last thing I want to do is just to slice up this array a bit and say that I want my X data to be all the rows in columns 0 to 9. And the Y data, which I'm trying to predict, is going to be rows 9, like so. And then I'll just return X and Y. Now, if we set a breakpoint here and run, maybe I should call the function also. So let's just stop plotting this and say that I want X and Y to be equal to structured input of my, let's actually call this something more useful. Call it simulated, like so. And I want to shift those 10 times. That means that my neural network eventually is going to have 9 inputs, because I have 10 columns and I use everything except the last one as inputs. So now if you look at this n matrix here, we'll see how that shift operation behaves using this thing here, and then use array in PyCharm. If you use another Python editor, then I'm sure it's going to be also there ways to look at the arrays. So notice how this is the 0th row, 0th column, sorry. That's basically the first 990 elements of my time series. So here. And then the first column is going to be value or time step 1 to 991. The second column is going to be time step 2 to 992. And third one is going to be 3 to 993. And then the last 10th column is going to be my final 1000th time step here. So this time step here is going to be what I have in my data vector here. So if you look at input data, you see 0. That ends up over here, and then this value is the same as this one, this value is the same as this one, same as this one, and so on. That's the value from the second time step, goes here in column 0, here in column 1, and it's not at all in the last 8 columns. If you look at this value, number 10 here, at 11th time step, 09471, that's going to be in the 11th column, in the 11th row in the first column, which is just a copy of the original data up to the kth last time step. And that same value is found time shifted by 1 in each column. So in this way we see that we can restructure a time series data set, or a time series sequence of data into a table like this, where at each column is just shifted by 1 more time step back in time like this. And then we can use these time steps here to predict this. We can use these time steps here to predict this, and so on. So that's why we have our Y data here as the column number 9, and the X data is column number 0 up to but not including 9. So this is going to be our X data, and this is going to be our Y data. So if we look at X, we see that this is then up to column 8, and Y is the last column here. So that's going to be equivalent to this one here. I hope that's clear. I also encourage you to look at the video on neural networks in general, where I will explain a bit more how this auto-regressive neural networks actually operate. That's the restructure of data. So now we have our data set here, which is what we need in order to start applying some machine learning to this problem. So to do that, we're going to again use the sequential API. And then we remember from the previous video that we can instantiate a model like this. Now we're going to add first one hidden layer, which we're going to do a dense layer, say 10 neurons. Again, I'm just guessing. We have to do some tuning on the hyperparameters later, and we're gonna guess that we can use the activation function hyperbolic tangents, and as in the case of the iris dataset, we have just one output, so we need an output layer like this in order to collect our neuron predictions or neuron outputs into just one. We also need this compile method to be called, as we saw in the iris video, and we're going to use just the same settings as we did there. So we want to use the mean square adder like so, and we want to use the Adam optimizer, and we want to output the accuracy metric. And then the final thing is just to fit our model to our X and Y dataset. And we're gonna run for, I don't know, what, 1,000 epochs maybe. And I want to turn off the verbose, so we don't need to look at all this printed text every time we run this. So, of course, this is not going to really say very much. It's just going to run the training. But at least we'll see if the code runs. Looks promising. It's not crashed yet. Yes, process finished. Good. Maybe we run once with the verbose off to see what happens here. So now we see that every epoch we get a print here where it says the runtime in microseconds per step. It gives us the value of the mean square error loss function, which you see here is going to be reducing somewhat. So you see here the training effect that we are starting out with randomized initial weights, which is going to be a pretty bad fit. See here we have an error of 0.7. After just one iteration, we are down to 0.14, then 0.04, and then it goes gradually down. So this is the optimization effect, that weights are being manipulated by the Adam optimizer to reduce the loss function. It's fitting this network to this exponential function data after we have performed this restructuring. So this is then 9 inputs, which is all this time shifted time series. And just to check what this is actually doing, we can do a prediction using the same training data. So of course this is not something we normally do, predicting our training data. We expect that predicting our training data is going to give very well behaved results. But just to see what actually happens here, we can still do it. And we do another plotting, where we now plot first the data that we have used in the original. So the data that we have used for training, which we're going to plot those in red. And we're going to label them as train. And then we're going to do here the y predict. Let's do that in blue. Call those predict, and then we're going to show this plot. Now I want just to turn off verbose like this because it's quicker. Now we will see the performance of this neural network that we have constructed and trained. Yes, look at this. I should also show the legend. But we see that the red is the training data. So that is the original time series behavior from the simulated data. And the blue data is the predictions of our neural network. So that's now taking as an input for prediction the exact same data that we trained. And we see that we get the behavior which quite closely fits the actual output. So that means that our model is able to predict what's going to happen one step forward by actually taking in the actual X data. We can maybe improve the performance here a bit. Let's say change to 4000 training epochs. See what that looks like. Takes a while to run 4000 epochs, but that's part of the fun with neural networks and training. It's sitting waiting for the computer to do its work. Yeah, so we see even with 4000 epochs, the performance isn't very much better. So that's an indication that at 1000 epochs, it's already sort of as good as we can reasonably expect with the structure that we have. So maybe another option would be to add a second hidden layer. Let's say just randomly choose 5 neurons. Go back to 1000 epochs. Also, let me just actually show the legend here to make it easier to see what's what. Yeah, so with a slightly more complex network structure, we get a much better fit. So what that means is that the initial structure we had with 10 neurons in one hidden layer is not sufficiently complex, means it doesn't have enough description power to represent this exponential function effect, even just predicting one time step ahead. We need a slightly more complex neural network, at least using the settings that we have now. Of course, you can play with these settings yourself and see if you can come up with other structures and other hyperparameter settings that work better than this. So one last thing I want to do is try to run this now with a different time constant. And then we're going to call this just like that, xsim2. And then I want to restructure this also in order to get now an actual test set for validating. So now we're going to do this like so. Didn't work so well. Let's do it by hand then. So now I'm just going to have a separate training sets, which of course you know from the videos that you should always do. But for tutorials we don't always follow the rules exactly. But now we're going to do like this. So now we have a training set and a test set. And we're going to do y predicted like so. And then we're going to do another prediction on the test set as well. And then we're gonna do these things again, but also for the test. Yes, we can do green and to see how that works. So what we change now is that we do the training on the X train, Y train, and then we do the X test on the prediction, and we compare to the Y test. See how that works. Yeah, so see that it's actually quite successful. We have the training here in the red and the blue. We see that the performance there is quite good, and it's similar to the test set actually. So in the test set, where we just run the same thing with a different time constant, we get more or less the same errors. It looks similar. And we see that we are running with a test set. The time constant is 2, which means slightly lower or slightly slower dynamic response to the changes in input. But we are still more or less able to track this change in state and making the one step ahead predictions. So that's it for this video. I hope you have understood at least somewhat how to use neural networks for doing auto-regression predictions. There's of course many more things we could do here. We have not looked at how to predict multiple time steps into the future. There are ways we can make the predictions be sort of recursive, that we use predicted values to predict future values. There's many more things here which we could cover. Please do send me requests if there is things you would like to see examples or tutorials on, and I will try to come up with some instructive examples for other variations on neural networks as well.